Well, good morning, Math 1. Honors Math 1. This is Mr. Roberts at Shasta High School, and I'm going to step through the study team test that you took recently. And hopefully, if you were confused when you're sitting there with your group, you have a chance to kind of think about these things kind of on your own, reflect, and prepare for the test we'll be taking relatively quickly. So question 1 on page 1 says, give the equation of a line that matches the given information. The very first part A, says, hey, this line has a y-intercept of 7/9 and a slope of -2/3. So that would be the line y is equal to -2/3 x, because my slope parameter is -2/3, and my y-intercept parameter is at 7/9. So there we go. That's part A. Part B says this line goes through the point 12,4 and has a slope of 3/4. So I do know one of two parameters, right? If I'm looking at slope-intercept form of a linear equation, I've got two parameters. I've got the slope parameter and I've got the y-intercept parameter. And I already know the slope parameter is 3/4. The parameter that I don't know is my y-intercept. However, I do know a point that lives on the line. I know that when x is 12, y will be the number 4. So what I can do is, look at this line, y equals mx plus b. If that's a line, right, where I've got the two parameters there, it's certainly true. If that's true, it's certainly true that y minus the product of m and x will equal my y-intercept. So what I'm going to do is figure out what my y-intercept is by plugging in a particular point that I know. Y is 4 when x is 12, and my slope value. So I'm just going to write y, which is the number 4, minus my slope, which is 3/4, times the x value of 12, and that will be my my y-intercept parameter. 12 divided by 4 is 3, and 3 times 3 is 9. So I'm looking at 4 minus 9 should be b. Therefore, it looks like b should happen at -5. Now that I know this, let's write the equation down, right? The equation should be y is equal to 3/4 times x, and then minus the value of 5. Now, one thing I might want to do is just verify, hey, is everything matching here? Do I have the correct slope? Well, yeah, my slope parameter is 3/4, and the slope should have been 3/4. And if I give this equation 12, does it give me back -5? In other words, if the input to this function is 12, does it produce a value of 4 rather? Does it produce an output of 4? Well, yeah, if I put 12 there, this is 3/4 times 12 minus 5. 12 divided by 4 is 3 times 3 is 9, and 9 minus 5 is indeed 4. So yes, when I give this function an input of 12, it gives me an output of 4. So, once we have something, if you've got any way of kind of like playing, checking, testing, seeing if it works, go with that. So that's part B. Let's look at C. C says this line goes through the point -2, 8, and 6, 4. So when x is -2, y should be 8. And when x is 6, y should be 4. So we don't know our slope. However, we do know that our slope is our change in y values divided by change in x values. So it's a common error to get these to get the reciprocal of the slope. So when you're doing this, please slow down and make sure you're getting the correct values. So we're going to say change in the y's divided by the change in the x values. My y values, of course, are these ones that I've underlined with this yellow color, and the x values are the ones that I've underlined in this green color. So if I look at this, change in y, I'm just going to take 8 minus 4. 8 minus 4. You can see I've taken this first value and I've subtracted 4 from it. 8 minus 4. And I'm going to follow the same pattern in my denominator. I'm going to take the -2, the first one I have listed, minus 6. That order matters. Only to the extent that you have to be consistent. So if I flipped both of them, I would still get the same slope. But if you do 8 minus 4, that first point minus the second, you have to do -2 minus 6. In my numerator now, I have 8 minus 4 is the number 4. And negative 2 minus negative 6, or I'm sorry, negative 2 minus 6, not minus negative 6. Negative 2 minus 6 is negative 8. So I'm looking like I have a slope of negative 1/2 if I reduce that. So I know my slope parameter, my m value is 1/2. What I don't know is my y-intercept. However, I remind myself y equals mx plus b. Oh, if that's true, right, for any line, that the y values will always equal the slope parameter times x plus the y-intercept parameter. If that's true, then it's certainly true that y minus the product of m and x has to be b. So I'm going to take any one of these points, and I'm going to just go ahead and use this point, right? I'm going to use my y value of 4 and my x value of 6. So watch how I plug these in. I'm going to say 4 minus, and then I have to be careful here. I'm going negative 1/2, so I'm using some extra parentheses. So y minus negative 1/2 times my x value, which is 6. 6 will give me b. So this is going to be 4 minus a negative 3, 4 minus a negative 3, right? If I multiply negative 1/2 times 6, I have a negative 3. So this looks like 4 plus 3, or 7. So my y-intercept should be at 7. Now, a lot of things happened here. Let's go ahead and write down the equation of this line. I believe the equation is y is equal to negative 1/2 times x, and then plus the value of 7. So I believe this is the equation. And I'm going to check this against both of my points, and I think I'm going to do this using the classroom calculator. So let me grab the calculator here. There it is. So let me, oh, wrong one, clear this. There we go. So if I'm looking at this, how could I check this value? Well, I'm going to go ahead and enter the equation itself. So yeah, let me show you this. So on these equations, there's a button right here that's labeled table. If you see this, now why? There it is, table. So when you press table, it says enter function in x. So my function is y is equal to, and I'm just going to hit negative 1/2. So there's my negative 1/2. Leave the denominator by hitting this. This button right here will give me a variety of variables. I'm going to press it to get my x, and then plus the number 7. Enter. At this point, I'm not going to leave it on auto. I'm going to have it start at 0 step by 1, but I'm going to come out here to where I'm going to select ask what x is, and I'm just going to hit OK. Now, of course, none of this is required. However, watch how efficient this is. If I give this function that I entered the number negative 2, you can see it gives me, oh, x has to be 8. If I give it 6, it gives me, oh, that's beautiful, right? And also, I know, because I know the y-intercept is 7, if I give it 0, it should give me 7, and it does. And every single time I enter another value up, it should decrease by a half. Or if I go up by 2, so I give it, instead of a 0, if I give it 2, it should decrease by 1, and it gives me 6. So it's a nice way to kind of just verify that, yeah, this equation is behaving exactly the way it should. Y equals negative 1/2 x plus 7 is absolutely the equation. If you're interested in this, using the table to check a particular equation, talk to me about it in class. Let's move on. Next question. It says this line is represented by this partial table. So one thing about this table is my x values are not increasing by 1. So I can't just simply look at this and say that a change in y is going to be the slope. And I have to look at a change in my y values, right? A change in my y values. And I'm going to have to divide that by a corresponding change in x values, right? A corresponding change in x. So same sort of deal here, right? Slope will equal that change in y. So I'm just going to go with the negative 4 minus 8. You can see it's a difference between negative 4 and positive 8. So I write negative 4 minus this positive 8. And in my denominator, I'm going to enter a -2, and I'm going to subtract from that a -6. So numerator, just -4 minus 8. Denominator, -2 minus -6. In the top, it looks like I've got a -12. In the denominator, it looks like I've got -2 plus 6, which I believe -2 plus 6 is going to be a +4. -2 plus 6. Yeah, it's going to be a +4. And -12 divided by 4 is -3. So I believe my slope parameter m is equal to -3. So what do I do now? Well, I've got to figure out what my y-intercept is. And I keep repeating this just because I want us to hear it a lot and get comfortable. Hey, if I can represent a line on the Cartesian coordinate plane, all of them except for the vertical ones, as y equals mx plus b, certainly if I know a point that lives on that line and my slope, I can find the y-intercept by subtracting mx from each side. So my y-intercept b is just y minus mx. Does not matter which point I pick to figure out my y-intercept. I've got tons of points. In fact, I'm going to use that top one. It's a 35. So I'm going to write y, which is 35, right? I'm using this y, minus m, and my slope is -3. So I've got minus m, -3, times x, which is -15. Oh, that's all kinds of fun. When I multiply -3 and -15, I get +45. So this looks like 35 minus 45. And if I consult with the calculator, I think 35 minus 45 is -10. Just kidding, I didn't need a calculator, did I? So now I know my y-intercept b is at -10. So equation should be y is equal to -3 times whatever the x value is, and then just subtract 10 from that. Alternately, a really quick way to check the work without using stored equations is just to say, oh, here we go. If I take -3 and I multiply by any of these values, for example, -6, -3 times -6, and then I subtract 10 from that, I should get what y is, and I do. I got 8. Let me do the last one. -3 times this 5. -3 times, ooh, why did I hit -5? -3 times 5, and then if I subtract 10 from that, I should get -25, and I do. So you can see this equation is doing a fabulous job of producing the correct outputs when I give it certain inputs. Still on page 2, the second question says, what was it? It says, given the input, identify the output for each of these functions. So the very first function is, it takes inputs of a value, and it looks like it squares that, then doubles that, adds 18, and then it takes that entire, that sum and divides it by 12. So one of the places where I saw perhaps some error was when we write this down, right, 3, I almost always will use, oops, not 3. It starts with a 2. 2, whoops, 2, open parentheses, 3 gets squared plus 18. And once I know what that is, I'm going to divide it by 12. A few errors of this nature, of multiplying by 2 first and then squaring it and getting a +36. But we know exponentiation comes first, and if we enter this pretty much like it appears on our calculator with the parentheses, it should give us the correct answer. But 3 squared is 9, so I'm looking at 2 times 9 plus 18. 2 times 9 is 18, so I've got 18 plus 18, and both of these are divided by 12. 18 plus 18, I believe, is 36. Yeah. So I've got 36 divided by 12, which is the number 3. So interestingly enough, for this particular function, if you give it a value of 3, right, if you feed 3 into the x spots, right, and then evaluate this expression, it gives you a 3 as an output. So when 3 goes in, 3 comes out. That's the answer for A. Let's go to B. Oh yeah, this was a little bit more problematic. So let's be real clear here. X is -4. Sorry about that. X is -4. So if I wish to square that, right, I'm going to show that like this. That is what X is, and I'm going to square what X is. So if we just enter this and then we type that on our calculator sees that as the opposite of 4 squared. It's not squaring the -4. It's basically squaring the 4 and then taking the opposite of that and giving you -16. This problem says, hey, you've got to square what X is. What is X? X is -4. So I have -4 getting squared minus 4 times, what's X? -4. So when I square -4 times -4 is +16. And then I have a minus a 4 times -4, which is, I've got 16 minus -16, which means 16 plus another 16. So when -4 gets fed into that function, it produces an output of +32. And shouldn't need it, but you know what? You know I use it occasionally anyway. So if I was to verify this with a calculating device, I might say, okay, a couple ways I can do this. This is a fun way too. On this particular calculator, if I want to store X as -4, I say, hey, here's -4. Store that into X. Enter. So let me show that again, because this is powerful. -4 is going to get stored into X. Boom. At this point, my calculator thinks X is -4 until I tell it something differently. If I press X, it's going to say that's -4. If I say 2 times X, it's going to say that's -8. If I say, oh, take X and square it, literally that's going to be a -4 times a -4, and it'll produce a +16. So my calculator thinks X is -4. So what I can do is I can simply say, hey, X is going to be squared, and then I'm going to subtract 4 times X. And when I do that, my calculator says, oh, I got you, that's exactly 32. Alternately, if I wanted to evaluate this without using this storing X thing, I could do this. I could do open parentheses, -4, close parens, square that, and then subtract 4, open parens, times a -4. And when I do this, it says, surprise, syntax error. Oh my goodness. It says syntax error because that needs to be not a -4, but it needs to be subtract 4. You know what? I think my calculator actually told me where that error was. So this now says -4 gets squared, and then subtraction 4 times a -4, it says also 32. So both ways seem to work just fine. Let's move on to our second page. On the second page, it says, hey, here's a function. And the question is, what value of X would I give this function so that it would produce an output of 55? And one nice way of doing this is just saying, hey, let's just take the function's definition. This is what the function does with X's, and say, hey, let's just set that definition equal to 55. So I can say 7 minus 3 times the quantity of 2x minus 4, and that has to equal 55. So what I'm essentially doing here is I'm saying, look, I've got to find the value of X that will produce this 55. And at this point, I'm just solving a linear equation, right? 7, -3 times 2x is going to be minus 6 times x. -3 times -4 is going to be plus 12. If I combine 12 and 7, that's 19, right? 12 and 7, 7, 8, 9. So I have -6 times x plus 19 has to give me an output of 55. And I don't know, I haven't had enough caffeine, and I'm going to use a calculator. So I'm going to take 55 and subtract 19 from both sides. When I do that, I get 36. So -6 times x is a positive 36. And then finally, I'm just going to take the 36. And yes, I'm doing it on a calculator, but I know the answer. The answer is going to be -6. But 36 divided by that -6 is going to give me a -6. So, and I like to write this step down. X is 36 divided by -6. X is -6. So if I take -6 and I feed it into this function, it should produce 55. And hey, I got time. Why not quickly just check that out? So I'm going to go 7 minus 3, open paren, 2, and then I'm going to enter open parentheses for x. So open paren, -6, close, minus 4, close. So I have exactly what? 7 minus 3 times the quantity of 2 times -6 minus 4, and I get exactly, hey, 55. So it turns out, yes, when you do give this function -6, it does produce an output of 55. -6 produces 55. Let's move on to part B. Part B says, where'd you go? There we go. Part B says, what value of x? Oh, Mr. Roberts, this is, wow, this is pretty straightforward. So take a look. 3x is 12. So I'm asking myself, what value of x? Let me pause this. I don't want to listen to the whole Ponderosa song. Those minute-long bells can be a lot. So if I solve for x here, I'm just going to divide both sides of this by 3. When I divide this side by 3, right, 3x over 3, you can see there's a giant 1 there. This just becomes x. On the other side, when I divide by 3, I get 12 thirds. And I happen to know that 12 divided by 3 is 4. So when x is 4, this clearly produces an output of 12 because 3 times 4 is 12. So that was part B. Let's move along to the next question. Next question says, simplify each expression. I've indicated that we're going to see questions like this almost all year. So big picture here, I have 3 things that are being multiplied, a 7, something else, and something else, right? 7, something else, something else. And if you're multiplying any 3 things, it doesn't matter the order in which you multiply them. So for example, if I have 2 times 3 times 5, I could multiply the 3 times 5 first and get 15. Then when I double it, this would equal 30. But instead, I could also go 2 times 3, which is 6 times 5, and I would also get 30. Or I could go 2 times 5, which is 10 times 3, and I would get 30, right? The important thing is that I'm multiplying 3 different things, and because of the commutative property, or you could see the associative property multiplication, I could go ahead and multiply any 2 of them first and get the third one. One error that I did see is, and I think I'm not exactly sure what this is, but I think because some of you saw the 7 here, a couple of you multiplied by 7. 7 somehow got squared. And I think I know what the problem is. I think if I had, for example, 7 times the quantity of 2 plus 3, right? 2 plus 3 is 5 times 7 is 35. That's 35. When I'm distributing, I can distribute a multiplication problem across an addition problem. Now this is useful if either the 2 or the 3 is an x and I don't know actually what value it is. It's not necessary here because I would just add 2 and 3, get 5. 5 times 7 is 35. But I think this is where we see where we think that if I wanted to distribute this, right, that would be 14 plus 21. 14 plus 21 is 35. So I think that's why we're here we do need to multiply both of them because they're terms. There's a difference between terms and factors. These are factors, right? So I'm not going to introduce an additional factor of 7. It's just 7 times something else. So I'm going to elect to multiply the first thing, the second 2 things. I'm going to multiply these first. And when I do that, I have an x squared. Whoops, I'm going to get rid of this arrow. I have an x squared times an x to the 4th. And if I multiply x squared times x to the 4th, that's exactly 6 factors of x. So it's x to the 6th power. And then I have this y to the -4th times y to the 9th. And if I multiply those, I get y to the +5th power, right? So those factors of y can live in my numerator. Oh, not x. I get y to the 5th power. And then there's just a single factor of x, right? It's not 49. It's not 7 in front of each one of those. It's just 7 times x to the 6th, y to the 5th. Let's look at B. On B, quite a few of us looked at this and we saw x to the third over x to the negative third, and we incorrectly identified that as a giant 1. So to be clear, if I had x to the third over x to the third, right, they were both positive, that would be exactly 1, but that's not what I've got. So let's go ahead and just do the 12 divided by 4. That's 3. So I've got 3x to the third over x to the negative third. So a couple of ways I can deal with that. On the board, we've got one of what's the quotient rule. If you have the same basis, I'm just looking at the x's. If I've got x to the third divided by x to the negative third, that's equivalent to x to the 3 minus negative 3, right? X to the 3 minus negative 3, which is what? It's x to the 6th power. So this ends up actually being x to the positive 6th power. And we'll talk about this more in chapter 3 as we progress through it. But for now, 3 minus negative 3 is 6. So this is 3x to the 6th. And one other thing you might want to consider is just spend a little bit of time with your calculator and just play with it and see what happens. So for example, if I have any number in a denominator, so 1 over 5, and I raise that to a negative 1 power, right? What is that? It's not negative 1/5. It ends up just being 5 over 1, right? 1 over 5 to the negative first power is just 5 over 1, or 5. If I have 5 raised to the negative first power, that becomes 1/5. So understanding that negative exponents, right, what are they doing? They're getting me some reciprocals and trying to play with what's happening there. The more we do that, I think the less friction we'll have for problems like this. So B was 3x to the 6th power. Let's go down here to D. Oh, actually, this is great. If I think about this, I've got something raised to the negative 2nd power. So on this calculator, I'll look at this something. I'll just say 8 raised to the negative 2nd power. So look what happens. It's going to become 1 over 8 squared. It's going to become 1 over 64. 1 over 64 to the positive first power, or I could say 1 over 8 to the positive 2nd power, right? That's exactly what that is. So these are equivalent to each other. And observing that, right, I can say, you know what this is? This is going to be 1 over 2x to the 5th raised to the positive 2nd power. At this point, right, we're pretty comfortable with what does it mean to square something. I'm going to have exactly 2 copies of those factors, right? I'm going to have a 2x to the 5th, 2x to the 5th in my denominator. So that means that this is the same as 1 over 2x to the 5th times another 2x to the 5th, because there's 2 of those groups. 2 times 2 is 4, and x to the 5th is x to the 10th power. So what I have is 1 over 4x to the 10th power, and that was the answer for D, ABC. Was that the last one? Did I miss? Oh, I missed one. So that was D. Let's go back and do ABC. Here's C. C. You know, we've seen this enough that maybe we can say, look, if I've got something to the negative 3rd power, that's going to be the same thing in the numerator to the positive 3rd power, right? I'll convince you of that. Maybe I will, maybe I won't. But if I have, like, for example, 1 over 2 raised to the negative 3rd power, that should be just the number 8, right? Which is what? What is that? That's 2 to the 3rd power, right? That's 2 to the 3rd power. And if I want, I could say that's over 1, right? So look at it. All of a sudden, 1 over 2 to the negative 3rd is the same thing as 2 to the positive 3rd over 1. So that's what happens here. So if I want to rewrite this now, I've got a to the 5th over a to the 3rd. And in my numerator, I've got b to the 5th times b to the 3rd. That is going to be b to the 8th in the numerator. And I'm just going to quickly break up this a to the 5th just for visual effects. A to the 5th is a squared times a to the 3rd over, there's an a to the 3rd that still is living in the denominator. times b to the 8th power. And as I look at those and I identify them, that's going to be exactly a giant one right here. So I have what? A squared times b to the 8th. And that's the answer for this. A squared b to the 8th power. So with that, we've completed question 4. Let's go down and look at the final question on the second page. And it says solve each equation below for the given variable. I really appreciate it when I see your work that I can see you're already showing me evidence that you're checking your answer. So for example, once you find x, you know when you plug x into both sides of this equation, you should be getting exactly the value of 11. So let's go ahead and take a look at this. I'll start by using the distributive property, and I'm going to distribute this 2 across this addition problem, right? It's a x plus a negative 2. So I'm going to write 2x plus 1 plus a 4x, and then I'm going to have a minus 8. Right? 4 times negative 2 is negative 8, and that will equal 11. Over on the other side, on the left side again, I've got 2x and 4x, which is going to be 6 times x, and a negative 8 plus 1, or 1 minus 8 is going to be minus 7, and that should equal 11. If I add 7 to both sides, we're looking at 6x is the number 18. And then finally, if I divide both sides of this by 6, this side becomes 6, or just x rather, and this side becomes 18/6. 18 divided by 6 is 3. So I should get x is 3. There we are. I think I know what x is. This is not a difficult problem to check, but I'm going to go ahead and use the calculator just to kind of demonstrate. I want as many tools as we have for doing it. So let's pull up the calculator here. There it is. And I'm going to take and store. I'm going to hit 3. That's what I think x is. I'm going to store that in x. So again, my calculator thinks x is the number 3. So if I say, hey, what's x squared? It's going to say 9. Right? If I say 5 times 3, 5x, it's going to say 15. So you see what it's doing here. So let's check this. If I say 2x plus a 1 plus 4 times the quantity of x minus 2, close paren. So understand that this right here looks exactly like our original problem, right? So you can see by entering this, I'm looking at the left-hand side of the original equation. And what does this have to equal? It has to equal 11. And when I see that, I say, oh, yeah, absolutely. X, when x is 3, right? All of my algebraic steps that I do here, right, are correct, right? Because I verified that it produced the correct a solution, right? A value of x that makes this true, which means both the left and right hand side are 11. So definitely worth checking your work like this, especially if you feel like you've got adequate time. And then the other thing is it just will kind of help us catch errors that we might make when we're doing the algebra and reduce errors. Last question on this page is solve for x. Let me get this calculator out of the way. So again, a bit with the distributive property here. So I've got 4x minus 3x minus 6. That's a negative 3 times a positive 2 plus 11 equals, on the other side, 6 times x minus 30. What's that? That's 6 times negative 5. I can combine these. So this is just going to be an x minus 6 plus 11 equals 6 times x minus 30. And I know what you're saying, Mr. Roberts, you could have done more than one step. I can't, because when I do it, it makes it, I can hide my errors. So I really refrain from doing that. So this is going to be x, let's see, negative 6 plus 11, I believe is going to be a positive 5. And over here, that's going to equal 6 times x minus 30. I'm going to subtract 1x from each side. 5 is 5x minus 30. I'm going to add 30 to both sides. So this is 35 is equal to 5x. That means that 35/5 is x. And I believe if you take 35 and divide it by 5, you get that x is the number 7. So let's go back up and verify, is x equals 7 the solution? And to do that, I bring up my friend. I have friends, right? A friend. Here, meet it. Here's my friend. It's a TI-30XS multi-view. So I want to store that x, whoops, I have to hit the number. 7 is going to be stored as x. So now x is 7. I don't need to verify that. But if I would go 6 times x, it would give me 42. Yeah. Okay. So let's see if the left and the right hand side are the same. The left hand side should be 4 of those x's minus 3 times the quantity of x plus 2, close parens, and add 11. So on the left hand side, I get 12. On the right hand side, I have 6 times the quantity of x minus 5. When I do that, I also get 12. What does that tell me? I'll tell you what it tells me. When x is 7, both the left-hand side and the right-hand side both equal the number 12. And because 12 is 12, hey, that's a solution. What is a solution? It's a value of the variable that makes the equation true. And yes, when x is 7, it definitely makes this equation true because it makes 12 and 12. 12 and 12 are the same. All right, let's go into the last page of this study team test. All right, question 6 asks us to evaluate 2 different expressions, one for part A and one for part B. Both of them are using the values of A, B, and C. So let's take a look at this first one. It says evaluate this if A is -3, B is 2, and C is 2. So I'm just going to write 2 and then open parentheses, and then I'm going to place -3 in its own set of parentheses, plus I'm going to place this in parentheses also, 2, close parens, plus 5, and then over C, which is the number 2 plus 1. All right, so let's take a look at this. If I look at in my numerator, that -3 and 2 are going to combine to give me -1. So this is 2 times a -1 plus 5. And I think I can combine 2 and 1 in the denominator without making an error. So 2 plus 1 is 3. Now what do I have here? Well, this is these when they combine, right? The 2 times -1 is -2. So I've got a -2 plus 5, which looks like 3. And in the denominator there is 3. Oh, this is the number 1. So for A, we should get that expression is equal to 1 with those values of A, B, and C, right? If A is -3, B is 2, and C is 2. All right, last one for question 6, part B, is this expression. And let me zoom out so I can see this. Oh, where did it all go? Oh, I'm back at the beginning of the test. Here it is. Sorry about that. Mr. Roberts, you're getting car sick. Okay, so let's go ahead and do this. Open parentheses. I'm going to have 2 plus another 2, and we're going to square that, plus the number 4 minus 5 times 2. All right, well, 2 plus 2 is 4, and 4, positive 4 squared is 16. 16 plus 4, and then this is going to be minus 10. 16 plus 4 is 20, and 20 minus 10 is 10. So when I put those values in for A, B, and C, I should get 10. Now, I'm kind of the opinion that I should not show you this, but I'm going to show you this anyways, just to show you some flexibility that you have with this calculator. So I have values for A, B, and C, and I can set this up. This is an easy problem. Probably, I don't doubt that I'm correct, so probably more work than it's worth. But I'm just going to go ahead and take this -3, and I'm going to store that not as X or Y or T, but as or Z or T, but as A. So -3 is going to be stored in A. Oh, that's convenient. And then I'm going to take 2 and I'm going to store that in, not X, Y, Z, T, A, but B. But I didn't hit my store in B. Nope, B, there we go. So now B is 2 and C is also 2. I don't need to even store this. I could just use B for both, but I'm going to do it anyways. So 2 gets stored in there we go. Now that I know those 3 values of my variables, I can evaluate this expression pretty quickly. I just do open parentheses. I need to grab B. You can see it's probably more, this is definitely more work than this problem's worth. B plus, go grab C. If I go past it, I just keep clicking until I get to the one I want. I'm going to square that, and then I'm going to add to that plus 4, and then minus 5 times A, B, C. There we go. And when I evaluate that, it says, oh, that's great. You did all that for that? Yeah, I did. But I just wanted to show you some flexibility you have in this calculator, allowing you to store variables X, Y, Z, T, and A, B, and C. And if you want to clear them all, you can hit second, clear them all. Clear the variables, yes. And if you come up here and you evaluate this expression now, it's going to be like, oh, I see what it's doing. Apparently, if you don't assign it values, it thinks they're 0. So this is just giving me just the number 4. Great. Last question. Oh, and this is a good one. So this dimensional analysis thing, I'm really pleased with how well you guys are starting to understand this and how well you're performing on tasks that look like this. So good job, keep it up. I know it takes a while to get this, but I'm given a speed in inches per second. In fact, the speed I'm given is 308,000 inches for every, I'll just put per, I can just put per second, and I can put the number 1, it doesn't matter, but 308,000 inches per each second. And I want to convert this into miles per day. So when I'm finished, I want an answer that looks like miles in the numerator and day in the denominator. So bunch of ways I can do this. I'm going to start, and I'll use red for this. I'm going to start by converting the time first. So right now I've got inches per second, but I need to turn those seconds into days. So what I'm going to do is start with things I know. For example, I know that I'm going to want to have seconds in the numerator, and I know a giant one that involves minutes. In fact, I know that 60 seconds is the same as 1 minute. So to be clear, what am I doing here? I've taken 308,000 and I've multiplied it by the number 1. Multiplying by 1 doesn't change a value. It doesn't change what's happening. These are equivalent, right? Because I'm just multiplying by 1. I'm going to multiply by another 1. This time I want minutes to go away, and I know a conversion that uses minutes and hours, and it looks like this. 60 minutes is the same thing as 1 hour. And then one final giant one I'm going to use, it's going to have hours in the numerator, and it's going to have days in the denominator. And I know that 24 hours is the same thing as 1 day. So if you look closely, what did I do? I've taken 308,000 inches per second, and I've multiplied it times 1, times 1, times 1. So I'm not changing the quantity, right? This is still going to be the same speed, just expressed in different units. Before we go on and look at dealing with the distance part, let's just see what happens here. Seconds canceled with seconds. The minutes are canceled with the minutes. The hours with the hours. So what we're looking at now is days. So per days we've matched. Now we're going to do the same thing, right? We're going to continue this for the inches. And I think there's only 2 that we need. I'm happy to share these numbers with you on a test. And in fact, some of these things I will write on the whiteboard so that you'll see them. But we've discussed this a lot. Well, this one you know, so I'll use green now for the distance part. We do know I want inches to leave, so I'm putting inches in the bottom, right? I had inches in my numerator, so I'm putting inches in the denominator. And I do know that if I have a foot, I know that 1 foot is the same distance as 12 inches. And I haven't given myself enough room here, so I think I'm going to try and collect all of this. Can I do this? Yeah, collect this and just slide it over. Oh, that looks great. That's good enough. So I just have one more giant one I'm going to multiply by, and it's this. I know I want feet to go away, so I put foot up there, but I'm going to put feet. And I'm going to put a mile up here, 1 mile. And I know that 1 mile is equivalent to 5,280 feet, 5280. right? 5,280 feet. They're the same. And take a look at what happens now, right? I had inches before. The inches are gone. I made them into feet. I I had feet, and the feet are gone now. So the only thing that I have left is miles, miles. So look, this entire calculation, the only units that are left is I'm left with a mile in the numerator and I'm left with a day in the denominator. So this is miles per day. But what's the number, you say? Well, the numbers are all still here. And the numerator, I have 308,000. I have to multiply that by 60 times another 60 times 24. And in my denominator, I have to multiply by, let's see, 1 times 1 times 1 times 1 times 12. 12 times 5280. 5280. So we are definitely looking at miles per day, but I'm not doing that calculation. So let me grab my calculator, clear this, and I'm just going to go, I'm going to do this as a fraction. So I'm going to go in the numerator, I have 308,123 times a 60 times another 60 times 24. In the denominator, I'm going to enter a 12 times 5280. And when I do that, I get 420,000. So this is the same as 420,000 miles per day. So that's it, right? Miles per day. If you have a calculator that does not have this fraction key, you can't quite enter that, be careful. Always use some parentheses when you're doing the division problem like this. So in this first set of parentheses, it's your numerator. So you'd be putting the 308,000 times 60 times 60 times 24. And in the second set of parentheses, you're going to be entering the 12 times 5280. All right, let's look at the final problem on this test. And I think we saved the easiest for last, maybe, especially if we were able to do that last one. So on this one, it says, convert 125 gallons per week into gallons per hour. So we're going to be still looking at gallons, so that's not going anywhere, but we've got 125 gallons per 1 week, and we're going to turn that into gallons per hour. So I want the week to go away. So I can see week is in the denominator, so I'm going to put a week in the numerator. And I do know this. I know that 1 week is the same as 7 days, right? That's clearly the same amount of time. 1 week is equivalent to 7 days. Now I want days to go away. Days are in my denominator, so I'm going to put them in the numerator, days. And I know, and I can go to hours now. And I know that 1 day is the same as 24 hours. So if I look at what's happened here, the week I started with has canceled with the week. The day has canceled with day. The only units of time I'm left with are hours. So this calculation now is, in the numerator, I've got 125 gallons over 7 times 24 is in the denominator, hours. I think 7 times 24 is 168, I think. Is it? 7 times 24 is 168. Yeah. So you can write this as 125 over 168. But in a problem like this, I literally would, I probably would just take the 125 divided by 168, and I would express it as, it doesn't say what to round it to, so I guess it's up to you at this point, but I'm going to say this is the same as about 0.74, maybe you could put another one, 0.74 gallons per each hour, right? So it's the rate is actually, it's a little less than 1 gallon every hour, right? So 125 gallons in a week is about 0.74 right? 0.75, close to 3/4 of a gallon for every hour. Right, that's it for the study team test, right at 50 minutes. I hope you found this useful. And if you've got questions, please write down what you're struggling with, what you're thinking about, and come see me in class. Talk to you soon.